Hello students, today you are going to understand about discrete Fourier transform. So what is this discrete Fourier transform? Discrete Fourier transform is a computation tool which is explicitly used for frequency domain analysis. So if you have a discrete time signal x of n, which is represented as a sequence of numbers, and if we have to do frequency analysis on this, we apply discrete Fourier transform on this x of n. Now to understand that, let us understand frequency domain analysis and reconstruction of discrete time sequence. So here what you will be understanding is, given a discrete time sequence x of n, how to perform frequency domain analysis. So to perform frequency domain analysis, you have to transform x of n, which is present in the time domain, into frequency domain. Then we can do frequency domain analysis. So if I have a x of n, which is a time domain sequence, now I have to perform frequency domain analysis on this. So I have to apply a transform such that it enters into frequency domain, and here we can perform frequency domain analysis. Now when you transform x of n into frequency domain, here we get the spectrum of this sequence in the frequency domain. Now after analysis, if you want to get back your x of n, then you have to go for reconstruction of discrete time sequence. So let us see how this happens. So this entire process you are going to understand now. How to convert x of n, which is in time domain, to frequency domain for performing frequency domain analysis, and how to get back x of n from the frequency domain. So let us understand this step by step. Now for this, first I am going to consider a discrete time sequence x of n, which is non-periodic in nature. Okay. Now I am going to first apply Fourier transform on this x of n. So application of Fourier transform results in x of omega, which is equal to summation of n varying from minus infinity to plus infinity, x of n e raised to minus j omega n. So when you look at this expression, we can see that x of omega is a continuous function of frequency. Though we consider x of n, which is in time domain and discrete in nature, and which was non-periodic, but when you apply Fourier transform, we can see that the Fourier transform of the discrete time sequence is continuous function of frequency, and that is periodic in nature. Let us visualize that by taking an example. So I am just plotting the spectrum. Okay, this is omega and this is x of omega. So if you visualize x of omega, it looks something like this, which is a continuous function of the frequency omega. Now here is a problem, because I am transforming x of n, which was discrete, into frequency domain. So I expect our transformation also be too discrete, but here I am getting x of omega, which is continuous function of frequency. So this is not a convenient representation of x of n. So what has to be done? So the answer for this is, you have to sample x of omega to make it also discrete. Then after sampling, we get what is called as frequency samples, which are also discrete in nature, and that becomes convenient representation of x of n. So to make x of omega discrete, that is, to get discrete frequency samples in the frequency domain, we have to apply periodic sampling on this frequency omega, such that the spacing between the samples should be delta omega. So this is how it is being done. Okay, so this is how we are going to sample this x of omega on frequency. And as I told, the spacing between any two samples is delta omega. Now we have applied periodic sampling on x of omega on frequency to get discrete frequency samples. Now, as Fourier transform in the frequency domain is periodic in nature, if we consider the samples in the duration 0 to 2 pi, it is sufficient for us because it is periodic with respect to 2 pi radians. So, if you consider all the samples from 0 to 2 pi, then these are sufficient for our analysis. Okay, now let us find out how many samples we get in this duration. Let me indicate the number of samples as n. Okay, so n is equal to this fundamental period 2 pi divided by the spacing between the samples. Okay, now to indicate how many samples are there in this duration, I will be taking an index k. So this k tells us how many samples are there in the duration 0 to 2 pi. So here k varies from 0 to n minus 1 or 1 to n. Now from this I'll find out what is delta omega. So delta omega, that is the spacing between the samples, from that expression can be given as 2 pi by n. Okay. Now let me replace this in the previous expression. So let me call this expression as 1. Now here I am going to replace omega with 2 pi by n and the index k. So I get x of 2 pi by n into k, which is equal to summation of n varying from minus infinity to infinity x of n e raised to minus j. Earlier it was omega, now it becomes 2 pi by n k, this is n, k n. So here k is the index indicating the number of samples in the duration 0 to 2 pi. So it is 0 to n minus 1. Now let me call this equation as 2. Now this expression tells us what? This expression tells us that we are computing Fourier transform at discrete frequency samples. So discrete frequency samples are given by 2 pi by n k. So which frequency sample you are computing the Fourier transform, that is indicated by k. So we have transformed x of omega, which was continuous function of frequency, into the discrete frequency samples by applying sampling. Now after obtaining these discrete frequency samples, we have to reconstruct back, that is we have to get back our x of n. Okay, let us do that. Now this expression which has n varying from minus infinity to infinity, let us split this into infinite summation values such that every summation will have n samples. So I am going to do that. So it's an infinite summation. So I am going to break this into small parts such that every part has n samples. So from left hand side I am breaking it. I am going to take only few examples. Plus n varying from minus n to minus 1 x of n e raised to minus j 2 pi by n kn, this is pi. Okay. Plus I am just taking few examples. After minus 1 it is 0, n is equal to 0 to n minus 1 x of n e raised to minus j 2 pi by n kn plus n varies from n to 2n minus 1 x of n to e raised to minus j 2 pi by n k plus so on. Now this can be further simplified like this. So I have infinite summations in this duration. So why I have to write all the summations? So what I can do is I can use a summation with an index. So what I'll do, I'll use a summation with an index L, which varies from minus infinity to plus infinity, and I have this summation which has n samples. So I'll write that as n varying from ln to ln plus n minus 1 x of n into e raised to minus j 2 pi by n kn. Now in this summation, I'll just do reordering of the summation, and I'll change this n to n from n minus ln. Let us see after this what will happen. So remember this expression. So I'm naming this as equation 3. So I'm reordering the summation. So on the left hand side I have x of 2 pi by n k equals, so what is that? L was varying from minus infinity to plus infinity. Then n was varying from ln to ln plus n minus 1. And here we have x of n e raised to minus j 2 pi by n k n. So this is where I am going to reorder, and I am going to change the inner index from n to n minus ln. So let us see what will happen after this. And I am also changing the order of the summation. So n comes outside. So now after n varies from, I am replacing n with n minus ln. With this I get n equal to 0, a lower limit, and here n minus 1, and this is retained, L varying from minus infinity to plus infinity, and x of, since I am changing the inner index into n minus ln, this changes to n minus ln e raised to minus j 2 pi by n kn. Okay. Now in this you can observe one thing. So what is that you have to observe is, which I am going to mark here. So if you observe this, this indicates that this is the periodic extension of x of n. So let me call that as xp of n. So here I will write xp of n is the periodic extension of x of n, which is equal to summation of L varying from minus infinity to plus infinity x of n minus ln. So this is the periodic extension of x of n, and this repeats after every n samples. So the fundamental period of this xp of n is n. So this is the periodic repetition of x of n. Repetition of x of n. Its fundamental period is n. That means after every n samples, the signal is repeating. Okay. So now this summation I am going to replace by xp of n, and I am going to rewrite this expression. So after this, let us observe what we are going to get. So on the left hand side, I have x of 2 pi by n kn. Okay, and here I had n varying from 0 to n minus 1. The inner summation we have replaced by the periodic extension of x of n, that is xp of n, and what we had, e raised to minus j 2 pi by n kn. Now I am going to mark this equation as equation number 4. Now xp of n is the periodic extension of x of n. Now we'll expand xp of n using Fourier series. So expand xp of n using Fourier series. So let us see what we'll get here. Xp of n will be equal to summation of k varying from, now I am expanding xp of n using Fourier series. So I get k varying from 0 to n minus 1 ck e raised to j 2 pi by n kn. Here ck is the Fourier series coefficient. This is Fourier series coefficient. Now I have to find out what is this Fourier series coefficient. Let me give that expression here. What is ck equal to? Ck is equal to 1 over n summation of n varying from 0 to n minus 1 xp of n e raised to minus j 2 pi by n into k n. Okay, so this equation where we have applied Fourier series, I am going to name it as equation 5, and this equation I am going to name it as 6. Now after expanding xp of n using Fourier series, then after finding the Fourier series coefficient ck, now I am going to compare, if you just observe here, I am going to compare equation 4 and equation 6. So you can see there is similarity here. So you have n varying from 0 to n minus 1 xp of n e raised to minus j 2 pi by n kn. Okay, so comparing equation 4 and 6, we will get x of 2 pi by n kn equal to n into ck. So let us do that. So all this we are doing to understand frequency domain sampling and reconstruction of the time domain sequence. So I am going to compare equations 4 and 6 to get, what is that you are going to get? X of 2 pi by n k is equal to n into ck, or ck is 1 by n into x of 2 pi by n into k. Now this ck I am going to replace in the equation of xp of n. See here, this is our xp of n, right? Equation number 5. So here I am going to replace ck with the relation what I got after comparing equation 4 with equation 6. So let us replace that. So what was that? xp of n, I am replacing ck here, okay? So xp of n equal to, I had here summation k varying from 0 to n minus 1. So here I had ck, that ck I am going to replace with this. So 1 over n x of 2 pi by n k into e raised to j 2 pi by n k n. Now this is the actual equation what we were expecting. So here our idea was to reconstruct back our time domain sequence x of n from the frequency samples x of 2 pi by n k. But when you look at this equation, we are using the frequency domain samples x of 2 pi by n k, but when you are reconstructing, you are getting xp of n. What is xp of n? The periodic repetition of x of n. So though we have reached at this equation doesn't actually give us the solution. That is, this equation only tells us that we can reconstruct the periodic extension of x of n, but we are not able to reconstruct x of n. So in order to get back x of n, so let us see what we have to do. So as of now we have got only the periodic extension of x of n. Okay, so from the periodic extension of x of n, how to get back our x of n? So let us see that. Now before that, we have to understand what is the relationship between x of n and xp of n. The relationship, as already told, xp of n is the periodic repetition of x of n, and the fundamental period of xp of n, that is the period for which xp of n repeats, is n. Okay, so I am going to take an example and to show what is the relationship between x of n and xp of n, and after that let us analyze how to get x of n from xp of n. So by taking an example. Okay, so as of now we have to understand that we have got the reconstructed version of the periodic extension of x of n. So I am going to take an example. So I am going to take an example. So let me take a sequence like this. This is our x of n. So let us say it is having a few samples. Okay. Let the number of samples of this be L. Now I am going to expand this. So I am taking two conditions here for expanding. Our first condition is when the fundamental period of xp of n is greater than the number of samples present in x of n. Second condition, when the fundamental period of xp of n, that is n, is less than the number of samples present in x of n. Okay. So first condition I am taking when the fundamental period of xp of n is greater than or equal to n. Next I am going to take the fundamental period of xp of n is less for periodic repetition. Now since n is greater than L, let us see. So I am going to repeat the samples. This is the first sample, second sample, third, fourth. Now since I have taken n greater than or equal to, okay, so this is my n. Next, our x of n is repeating. Okay. This side. Now here you can see that n is greater than or equal to L. Still here if I take, it is equal, greater. Now from this, if you look at these two, x of n and xp of n, we can easily say that I can extract x of n from xp of n, because xp of n is the repetition of x of n. So in this duration, that is when our n is varying from 0 to n minus 1, so in this duration, when our n is varying from 0 to n minus 1, when we observe, we can see that our x of n is same as our xp of n. Okay, when n is greater than or equal to n. Now I am going to say take another condition where the fundamental period of xp of n is less than the number of samples present in x of n. So if I take this condition, let us see what we are going to get. I'm going to draw the periodic repetition xp of n. So this I'm going to take it as n. So here you can see that this is our n, and the number of samples in x of n is this. That is, if I count whatever example I have taken, so you can see that number of samples in x of n is 1, 2, 3, 4 and 5. But here the periodic repetition is 3. That means when xp of n is repeating, so it is trying to overlap. So the next part, that is when these three samples are when x of n is repeating, because the fundamental period is less, the last two samples are being overlapped by these two samples. So these last three samples, as you can see, are hidden in the first two samples during periodic repetition. So since the information is being hidden, so from this xp of n, we cannot get back our x of n, because this is aliasing condition. So here the last two samples of x of n are being overlapped. So this is aliasing in time domain. So I think you are able to understand. So these two samples and here these two samples are being overlapped. So you can see these two samples are not present. They are being overlapped during periodic repetition. So those two samples are lost. So every time the signal is repeating, these two samples are lost. I mean they are hidden. They are being overlapped. That is called as aliasing. So here I have shown two conditions of periodic repetition, when n is greater than or equal to n and when n is less than l. So from this, what we can understand is, now if I want to get x of n from these periodic repetitions, I can get when n is greater than or equal to l, because n is sufficient. Here n is sufficient, that is it can accommodate all the samples of x of n. So whenever your xp of n periodic repetition, that is n is greater than the number of samples of x of n, we can extract x of n from xp of n. But whenever n is less than the number of samples present in x of n, we cannot extract. If at all you extract, that is you are losing some information. So from this example, we can come to a conclusion that xp of n is equal to x of n in the duration 0 to n minus 1. So coming back to the previous slide. So what was there in the previous slide? We were trying to reconstruct our x of n. We were trying to reconstruct our x of n from the frequency domain samples. So from the frequency domain samples, we have reconstructed xp of n. Now from xp of n, I have to get back my x of n. So with the example what I shown, so it is easily understood that from xp of n, I can get x of n when n is greater than or equal to l. So with this, finally, I can write. So with the example whatever I shown, so finally I can write. So let me recall that expression. So I had shown this xp of n is equal to summation of k varying from 0 to n minus 1. I had 1 by n here, and here x of 2 pi by n into k e raised to j 2 pi by n k. So after xp of n, we have to get x of n. So from xp of n, I will get x of n. How? X of n with the previous example what I shown. You can write x of n is equal to xp of n provided our n is greater than or equal to n in the duration n varies from 0 to n minus. Okay, so this concludes the topic that from x of n we have got the frequency domain samples. From the frequency domain samples we have got our time domain sequence x of n. So in this class you are able to understand the discrete Fourier transforms, frequency domain sampling, and how to reconstruct back the x of n. Thank you.